Hello, this is Dr. Hassan Abdullah. I'm here with the course Data Structures and Algorithms, and the supplemental material for this course is available at easymcq.com /goget. So this course consists of 10 topics which are in the screen in front of you, and we are right now in the topic of trees. And these topics are further divided into subtopics. The subtopic which we will be covering in this lecture is B trees or balanced trees. So now I'll move on to the supplemental website. So you can see the supplemental website easymcq.com, and there are quite a few cutting edge courses available, full length courses available in addition to data structure and algorithms. The courses like natural language processing, machine learning, and you can check all these courses. So let's focus on the course which we are doing right now, which is data structures algorithms. So there are quite a few topics in this course, and we are looking at the topic of trees. So instead of diving fully into the topic of tree, the approach which I have adopted is going through subtopic by subtopic. So this this video lecture is about B trees. So B over here does not mean binary. It can be a fivery tree of four or whatever the branching factor could be. B over here means balanced tree. So this is a perfectly balanced tree, and there are many benefits of having such a balanced tree. So, but it is instead of calling it a balanced tree, usually the terminology which it goes by is a B tree. So, B tree or a balanced tree, there are certain characteristics of this tree. First of all, it is balanced. It means that the distance between a leaf, every leaf, and the root is the same. The distance, which is the hops, and then there is a certain node structure, and keys are stored in the node, number of keys. For example, the binary trees which we have been discussing, there is a single key stored at a node, but in a B tree there are multiple nodes, and those nodes can have multiple keys, and the key storage is there, and those keys are usually in a sorted order, and there's a certain relationship between the key values and their parents, and the height of the tree is usually a log of n, most usually, but always. And there are certain operations which are performed on a balanced tree, such as search, which is there, and insertion and deletion. So let me give you an example. Let me zoom into this example. So this is the example of a B tree or a balanced tree, and it has the keys stored in them, in the nodes. And you can see that unlike a binary tree, there are multiple keys stored in a node. Number one. Number two, the height of the tree is logarithmic, and the distance of every leaf, the distance. Let me draw it for you also. So the distance is like and two hops, one and two hops. So the distance is the same, right? The other thing is, let me clear this also. The other thing is that the distribution of the keys. As you can see that all the keys which are less than 20 are on one side or one subtree, and the greater than 40 are at the right subtree, and of course the values between 20 and 40, they are here. Of course the branching factor here is 3. It can be 5, it can be 7. It depends upon the nature of the problem. Okay, so this is not a binary tree, right? So this thing should be very clear. Let me clear this. Okay, sorry about that. Okay, this, all right. So what are the advantages of B trees? Advantages are numerous. First of all, efficient search, insertion, and deletion. This balanced tree is never going to be act like a chain, which was the problem in binary search trees. So that will always be balanced, and then for efficient search, insertion, and deletion. So all of these operations are going to take order log of n time. Then minimize disk I/O. I will show you a Q&A towards the end of this sequence of this lecture. So you will see that there is a significant performance degradation when we leave the main memory and go to the hard disk or the secondary memory. So when you minimize this disk I/O, there's a tremendous gain in the performance, and that is quantifiable also. This is the balance structure. So this basically supports why this is efficient because of the balance structure, which I have shown you before. So this is the balance structure, that the distance between the leaf and the root is the same for every leaf, right? And then is the dynamic growth. So this tree is not static. So as the keys are being added, the size of the tree grows, and the keys are added. And of course, for example, a key is added. Maybe the key will go over here, okay, and maybe the key will go elsewhere. So number of keys are added. Maybe there are other levels are also created. So this is a dynamic structure. and support for it. This is one of the beautiful and wonderful things, is that since the keys are arranged in sorted order within a node, so range-based queries, for example, in GIS systems, geographical information systems, that is of tremendous utility, because then we can find the results within a certain range. What are the applications of B trees? B trees has numerous applications. For example, this I've already mentioned, geographical information systems. Database indexing. So what is indexing? Indexing is basically uh, getting to what I am looking for, what I am searching for, without looking at every value. So if I have n values and I am searching for certain thing, so if I go through all those values, order n time is taken, that is not indexed. So B-tree indexing is extensively used in databases, and that helps give a performance boost, because B-tree indexing takes the query right where the data is located. And the file system access is also very useful in NTFS and HFS, so providing efficient access to the files. Then is the storage systems, which is basically indexing supports this storage, and the multimedia applications, when there are huge volumes of data like images and videos, helps manage the indexing. Okay, so instead of bringing the things back and forth, it helps manage the indexing. And geographical information system range queries. So if I run a query that looking for a restaurant, so if I get the results of the restaurant 100 miles away, they are not of utility. So these range queries will help me find those restaurants which are, say, like 10 minutes drive from where I am running the query. So this is of tremendous utility. Okay, so compare the latency. Latency is the access time, right? Is the access time of the hard disk with the RAM, random access memory. So the benefit of B tree or balanced trees is that it allows quick access within the RAM instead of going to the hard disk. Okay, let me show you some of those figures. So there is the average latency time. Latency time is the system to access the specific data. Okay, of course, now we have we have no solid state disks also, but they are still no match for a random access memory, because random access memory is on the motherboard within your box, okay, within the CPU box or the laptop body. So the seek time for a hard disk drive is 4 to 10 milliseconds, and then is the data transfer rate also, which takes the data traveling over the cable, right, which connects the hard disk or whatever that external disk to your machine. But random access memory is like 50 to 150 nanoseconds. So that is very, very fast. That is very, very fast. Okay. And of course, so the total difference is that hard disk is 10,000 times to 15,000 times slower than random access memory. So if you reduce the number of IOs, this is the kind of a speed up you get. Okay. And this I'm going to explain in the next Q&A. So these are the references. If you're interested in knowing more, so you can go to those references and get to know more about the speed access time, right? So this is for your help. So how disk IO issues are resolved using B trees? How they are resolved? By minimizing the disk access. Try to understand, because this is a balanced tree structure. Therefore, there is not going to be a chain, okay, and that chain basically degrades the performance first of all, and then is the ensures that the height of the tree remains logarithmic. Okay. Operations searching for a key can be performed in log n time. Then is the large node size. So because of the large node size, instead of going back and forth, the data which is to be searched, okay, that is in the node. So instead of traveling all the way from the root to some other node to a leaf node, okay, so the data, the keys are located in a sorted order within the node. So that is time saver. And sequential and efficient IO operations. Sequential access, efficient navigation. Sequential access, how come the sequential access comes? When adjacent nodes disk block pages are accessed sequentially. Because the addresses are stored, if you recall this image I showed you over here, yes. So these keys are stored sequentially. So the same way the blocks are also stored, corresponding blocks are also stored sequentially. So there is no back and forth movement of the hard disk head or its rotation. So that saves a lot of time, right? And then of course, what else we have? Efficient navigation is there. Root multi-level indexing root. This is very interesting. This is the multi-level indexing. So this is the first level of the index. Okay, less than 20 and greater than 40. This is the second level of the index, between 20 and 40. Okay, and then between 30 and 33. So this multi-level indexing saves a lot of time, right? So try to understand that if it was a binary search tree, the size of the tree would have been very large, right? And so this basically is the biggest advantage of this multi-level indexing also, and the access time. And then there are intermediate levels, and the leaf level also contain actual data, the pointer. So this is basically an example which I mentioned before. So this is a five-way tree, and there are 31 nodes at different levels. And how many levels? One, and there are only two levels. So we can create the number of levels and the size of the nodes as we require. And these are the pointers which actually point to the data. So this is all for this wonderful stuff on balance trees. Of course, there can be more also. And if you are interested, here's the reference for you to read more about it. So that's all for this lecture.